Alright, so for this video, we're gonna read 3 articles from Chips and Cheese. Uh, Chips and Cheese is a blog and article website for chips, electronics. And I'm not gonna understand anything. I'm not a computer engineer or an electrical engineer, so um, alright, I'm fine with being stupid. So probably takes 1 hour being stupid, but after that we get enlightened. Alright, so I only understand this part from the title of this article. Capacity. It's like capacity. Anyways, Cortex A73's not so infinite reordering capacity. Cortex A73 aimed to address the power and thermal issues that prevented ARM's early 64-bit cores from reaching their full potential. It started a trend that saw ARM successfully capture the smartphone CPU market and did so by emphasizing efficiency. Part of this effort appears to be a unique out-of-order retirement mechanism. So I believe this is one of the DDR4 chips fitting the Amlogic S922X4 A73 cores and other on-chip stuff. Out-of-order execution tries to mitigate the impact of memory access latency. This feature frustrated my prior attempt to dig into A73's architecture. Henry Wong's methodology for measuring structure sizes largely didn't work except for scheduling capacity. Muffiny McMuffin Face on Discord suggested blocking retirement with an unresolved branch, and that did the trick. Out of order retire. With conventional out-of-order execution, an in-order frontend brings instructions into the core. The rename allocate stage assigns backend resource to the instruction. Then the backend calculates results for those instructions without waiting to know whether the instructions. It's a hard article. Excuse me. The instructions actually need to be executed. These speculative results are contained in various internal core structures until they are known to be good. Register values are held in the speculative portion of renamed register files, and values to be written out to memory are held in a stored buffer. Finally, instructions can be retired. Leave the core when they have passed all checks, and all instructions before they have passed their checks. On retirement, register values are made program visible and pending stored data is written out to the memory hierarchy. Retirement also frees entries from internal code structures, making them available for newer incoming instructions. Therefore, how far a CPU can move past the stalled instruction is limited by how many entries it has in internal structures like register files, load, store, buffers, and so on. In-order retirement is a straightforward way to preserve the illusion of in-order execution, which programs and operating systems expect. If something funny happens, like a program accessing virtual memory that doesn't have corresponding physical memory map, the operating system expects to handle that exception with program state preserved right as it was before the offending instruction would be executed. Preserving the state lets the operating system fix the issue, for example, by paging to disk and resume the program as if nothing had happened. So conventional out-of-order execution is load, add, and then you have integer register file capacity, instruction retirement, freeing register file entries blocked by incomplete load. So incomplete, complete. I feel like which way are we moving? We are moving that way, I guess. Backend cannot accept instructions past this point. Cortex A73 Load retirement unit bypasses incomplete load. Add. Register file entries freed up for new instructions. Integer register file capacity. Add load cache. And now we have Cortex A73 detecting limits. Load cache miss branch. Add load cache miss. Backend cannot accept instructions past this point. Integer register file capacity. Retirement unit bypasses incomplete load but can proceed past unresolved branch. A CPU's backend can accomplish this by discarding, not retiring all instructions after the one that hit an exception. It can then show known good state at the exact point of the exception. If a CPU designer got smart and tried to retire an instruction out of order, the core could find itself in an unrecoverable state if an earlier instruction hits an exception. But A73 can do exactly that in certain cases, and at least one of those cases is an incomplete load. I suspect A73 can determine when a load is guaranteed to complete successfully. If address translation competes and access checks against the page table entry are good, there shouldn't be anything causing the load to fail short of a catastrophic memory subsystem failure. So we have the latency for 2 cache misses, and then you have an integer adds between cache misses, and then it goes at around 41, 42 to 100, from 100 between 150 to 200, what seems to be around like 170 to 275. In that case, A73 can start retiring instructions ahead of the incomplete load, secure in the knowledge that the results it's committing early won't have to be thrown out. However, A73 can do so past an incomplete branch because it doesn't know if it predicted that branch correctly. A branch mispredict doesn't require any attention from software, but the core needs to preserve results from instructions before the branch in order to recover. Therefore, Henry Wong's methodology can be modified for A73 by adding a branch dependent on the cache miss. To keep mispredictions from influencing results, the branch is never taken, working with a shoestring power and area budget. This modified methodology shows substantial shrinks to most core structures compared to A73's predecessors. So this is ARM Cortex A73. You have your branch predictor, you have your L0, L1 indirect target array, L1 return stack, and L2 return stack going to L1 instruction cache, 64 kilobyte 4-way. You have your MSHRs 4 and 3, your micro TLB 32 in 3. You have your L2 TLB 4K 100,024 in 3 4-way. Walk cache large pages 128 in 3 2-way. Then shared L2 cache 1 megabyte 16-way. And then you have 16 bytes cycle read, 32 byte per cycle write. And then you move from micro TLB. What is micro TLB in its chip? What is micro TLB? Translation look-aside buffer is a memory cache that stores the recent translations of virtual memory to physical memory. It is used to reduce the time taken to access a user memory location. It can be called an address translation cache. It is a part of the chip's memory management unit. Okay, so and then you go from memory subsystem up and down, and then you go to execution engine. Then you have your instruction control 8. You have your two-way decoders from the front end, and then you have instruction control 8 slots, branch, store. What was TLB? Translation load leukocyte buffer. Every B is buffer. Every B is buffer. Every B is buffer. Translation leukocyte buffer. So we have this scheduler 6 in 3, scheduler 6 in 3, scheduler 14 in 3, scheduler 14 in 3, and do we put this together? Maybe 28. 4, we have 34, 40, and then you have in the integer register file you have about 73 in 3, and then you have a ALU, you have integer multiplication, branch, address generating unit. And that was for finding the next instruction in the memory. And FMA, fused memory. What is FMA? It's fuse multiplication augment in chips. Fuse multiply add. Okay. Yeah, we already went through this one time, but it doesn't hurt to go over it. The FMA instruction set is an extension to the 128 and 256-bit streaming SIMD extensions instructions in the x86 microprocessor instruction set to perform fused multiply add operations. Alright, we can ignore this for now, maybe. Fuse multiply add FMA. And then what is AEC? What is AES in chips? Advanced Encryption Standard is an international standard which ensures data is encrypted and decrypted following this approved the standard. Alright. Okay, so you have your execution engine, your memory subsystem, and you have your front end. This is probably your caches. This is where you access your memory, your shared L2 cache. And then you have your scheduler 6 in 3, scheduler 6 in 3, scheduler 13 in 3, scheduler 9 in 3. And then, sure, that's good. On A57, register file entries where it's 32 bits wide to make register file storage go as far as possible. I suspect those early 64-bit ARM cores were expected to handle a lot of 32-bit code, and wasting the upper half of a 64-bit register wasn't ideal. 64-bit integer registers and 128-bit vectors were handled by allocating multiple 32-bit registers. A72 made register files entries 64 bits wide and improved FMA fused multiply add performance, which will require more register file storage and more ports. Register file area is mostly limited by the width and number of access ports, and not so much the number of storage cells per entry. A73 ditches that approach in favor of separate integer and floating point in register files. The integer register file has 64-bit entries with 41 available. For speculative results, FP/vector registers are 128 bits wide with 38 entries available for speculative results. Dedicated register files allow lower port counts from each register file when building Zen 4's FP vector register file. AMD was able to use 512-bit entries with minimal area growth because port count and width had a larger influence register file area than the width of each entry. ARM likely made a similar observation with A73. A unified register file with small entries would make the most of storage cell capacity. But that was the wrong way to go for area efficiency. It was probably the wrong way to go for power efficiency too. Alright, so Cortex A73. Let me just check what is Cortex. Cortex A73. So the ARM Cortex A73 is a central processing unit implementing the ARM V8-A 64-bit instruction set designed by ARM Holdings Sofia Design Center. The design of the Cortex A73 is based on the 32-bit ARM version 7-A Cortex-A17, emphasizing power efficiency and sustained peak performance. The Cortex A73 is primarily targeted at mobile computing. Okay, is this what's inside? I'm not sure what this is actually. Alright, so what is the SIP core? Semiconductor Intellectual Property Core. Is a 2-byte decode out of order superscalar pipeline. Superscalar. A superscalar processor is a CPU that implements a form of parallelism called instruction level parallelism within a single processor. In contrast to a scalar processor, which can execute at most one single instruction per clock cycle, a superscalar what does it say? In contrast to a scalar processor, which can execute at most one single instruction per clock cycle, a superscalar processor can execute more than one instruction during a clock cycle by simultaneously dispatching multiple instructions to different execution units on the processor. It therefore allows more throughput, the number of instructions that can be executed in a unit of time. This is really interesting, that how you can have a series of instructions and then you just figure out some way to parallelize them, and they also depend on each other. What the fuck? This is amazing. This is absolutely amazing. It therefore allows more throughput. Okay, so throughput is throughput, the number of instructions that can be executed in a unit of time than would otherwise be possible at a given clock rate. Each execution unit is not a separate processor or a core if the processor is a multi-core processor, but an execution resource within a single CPU, such as an arithmetic logic unit. While a superscalar CPU is typically also pipelined, superscalar and pipeline execution are considered different performance enhancement techniques. The former superscalar executes multiple instructions in parallel by using multiple execution units, whereas the latter pipeline executes multiple instructions in the same execution unit in parallel by dividing the execution unit into different phases. In the simple superscalar pipeline figure, fetching two instructions at the same time is superscalar, and fetching the next two before the first pair has been written back is pipelining. Alright. Okay. So, superscalar pipelining. Do you get that? And they have more throughput. I remember we had throughput in the other model for LLVM, if I'm correct. I feel like I'm correct, yes. He used throughput. So throughput is the number of instructions that can be executed in one unit of time. Well, for computer it's a clock cycle, so I figure that's what it is. All right. Besides being more efficient, A73. Were we here? Maybe not, but I'm gonna read over it again. Besides being more area efficient, A73's register file setup can give it an advantage in vector code. 35 vector register file entries are available for 128-bit results compared to 31 on A72. A73's advantage should be even more significant in practice because the scalar integer and vector operations won't contend for capacity in the same register file. However, A73 can perfectly allocate all entries across both register files and caps out at 66 in flight instructions. With an even mix of operations that write to scalar and vector registers. Other CPUs have similar limitations. Intel CPUs have a physical register claim table that tracks which register should be freed when an instruction retires. Lack of entries in that structure can cause a stall before all register file entries are exhausted. A73 may have a similar structure. Memory access and branches. A73 can have 50 in-flight loads, which is a massive compared to its other structures. In fact, 50 in-flight loads can only be achieved by using both integer and vector destination registers. Otherwise, reordering capacity will be limited by how much register file capacity you can reserve to hold loaded data. This is a substantial improvement over A72's 32 in-3 load queue, and is likely to be a relevant limitation in practice. Stores are a different story. Cortex A73 can only have 11 in-flight stores. What is in-flight store? Excuse me. Great. So I'm just gonna take a pause. Did you see that information wasn't on web? So that's exactly the issue with these AI agents. Like when it comes to the border of pushing the limits, there is no data. There's literally very, very limited data. And that's why you still need to have good skills and not rely on an external intelligence tool completely. Alright, that was just me being wise for 10 seconds, excuse me. If this resource fails, subsequent branches can get into the core even if a scheduled capacity is available. That creates a funny situation where A73 can have more incomplete branches in flight than complete ones. Perhaps stores and branches need to reserve at least one slot in some kind of 11-in-3 verification queue. If a slot isn't available, the incoming instruction can enter the backend even if a scheduler in 3 is free. Branches and stores both need extra care before their result can be committed. Branches can be mispredicted. Committing a store means writing its data to cache, making it visible to other cores. Whatever the case, this 11-in-3 buffer is likely a very hot structure. Capacity is low even if it's only used by stores. Branches will further increase pressure on those 11-in-3s. Memory ordering woes. Stores cause another problem for A73 besides taking up valuable space in a small structure. A73 doesn't have a way to speculate whether a load will be independent on a prior in-flight store. That means loads can be executed until all prior store addresses are known. Memory dependence prediction isn't new. Intel's first implementation was in the 2006 era Core 2, while AMD did so in 2011 with Bulldozer. It's a huge advantage because most loads don't overlap with the prior store. Loads that miss cache are among the highest latency instructions a CPU will have to deal with. A73's inability to do memory dependence speculation will cause loads to be delayed even when that delay isn't needed to ensure memory operations execute in the right order. That in turn will put more pressure on the core's limited reordering capacity. Reordering buffer. Yeah. Most out-of-order CPUs use a reorder buffer to ensure in-order retirement. The reorder buffer is a list of in-flight instructions being tracked in the backend and is kept in program order. Reordering capacity can be capped by the ROB's size if no other resources are exhausted first. A73 doesn't appear to have a structure. NOPs, what is an NOP? NOP assembly. No op. Okay, or command practical command that does nothing basically. Okay, no operation. Because they don't take space in the register file, load and store queues, or other more specific resources. They are just an instruction that does nothing, taking up a reorder buffer slot, but NOPs have basically infinite reordering capacities, even past an unresolved branch. Okay, what is ROB in microprocessor? Okay, this is from RISC 5, so okay, so maybe you can see it really like this. Make it bigger. The reorder buffer tracks the state of all in-flight instructions in the pipeline. The role of the ROB is to provide the illusion to the programmer that his program executes in order. After instructions are decoded and renamed, they are then dispatched to the ROB and the issue queue are marked as busy. As the instructions finish execution, they inform the ROB and are marked not busy. Once the head of the ROB is no longer busy, the instruction is committed and its architectural state now visible. If an exception occurs and the accepting instruction is at the head of the ROB, the pipeline is flushed and no architectural changes that occurred after. Okay, let's read from here to here again. And over here. As instructions finish execution, they inform the ROB and are marked not busy. Once the head of the ROB is no longer busy, the instruction is committed and its architectural state, no apostrophe here. If an exception occurs, an accepting instruction is at the head of the ROB, the pipeline is flush and no architectural changes that occurred after the accepting instruction are made visible. The ROB then redirects the PC program counter to the appropriate exception handler. So I'm gonna go blind, but here we go. So you have your PC, you have your ROB head, you have your ROB tail. You have an instruction bank, and you have an instruction bank 2, 0 and 1, and then it clears busy bit, and then you have com mask, com uops, this mask, this uops, execution units. Alright, let's keep reading. Why not? The ROB is conceptually a circular buffer that tracks all in-flight instructions in order. The oldest instruction is pointed to by the commit head, and the newest instruction will be added to the ROB tail. To facilitate superscale dispatch and commit, the ROB is implemented as a circular buffer with W banks, where W is the dispatch and commit width of the machine. This organization is shown in figure 16. Okay. At dispatch, up to W instructions are written from the fetch packet into an ROB row, where each instruction is written to a different bank across the row. As the instructions within a fetch packet are all consecutive and aligned in memory, this allows a single PC to be associated with the entire fetch packet. And the instruction position within the fetch packet provides the lower order bits to its own PC. While this means that branching code will leave bubbles in the ROB, it makes adding more instruction to the ROB very cheap, as the expensive costs are amortized across each ROB row. Okay, what is ROB row? Each ROB entry contains relatively little state. Is entry valid? Is entry busy? Is entry an exception? Branch mask, which branches is this entry still speculated under? Rename state, what is the logical destination and the still physical destination? Floating point status updates. The PC and branch prediction information is stored on a per row basis. The exception state only tracks the oldest known accepting instruction. So, do you want to read this completely? I don't know, but I'm starting to get it a little bit. Like, yeah, this is the thing. You need to learn the key. I think when you learn the keywords, the buzzwords, then you can map that concept way easier in your brain, and that basically enables you to be like MFA, FMA, FMA, or buffer BRO, ROB, and then so yeah, and then learning is like making a sand pyramid. You have to like push a lot more to get a little bit just taller. So that, yeah, you have to accumulate a lot of things, so you will remember the highlights of it, I guess. Alright, when the instruction at the commit head is no longer busy and it is not accepting, it may be committed. Its changes to the architectural state of the machine are made visible for superscalar commit. The entire ROB row is analyzed for not busy instructions, and thus up to the entire ROB row may be committed in a single cycle. The ROB will greedily commit as many instructions as it can per row to release resource as soon as possible. However, the ROB does not look across multiple rows to find committable instructions. Only once a store has been committed may it be sent to memory for superscalar committing of stores. The load store unit LSU is told how many stores may be marked as committed. The LSU will then drain the committed stores to memory as it sees fit. When an instruction that writes to a register commits, it then frees the stale physical destination register. The stale PDSD is then free to be reallocated to a new instruction. And then you have your exceptions and flushes. Exceptions are handled when the instruction at the commit head is accepting. The pipeline is then flushed and the ROB emptied. The rename map tables must be reset to represent the true, non-speculative committed state. The frontend is then redirected to the appropriate PC. If it is an architectural exception, the accepting instructions PC, referred to as the exception vector, is sent to the control status register file. If it is a microarchitectural exception, load store or ordering misses speculation, the failing instruction is refetched and execution can begin anew. Parameterization. Rollback versus single cycle reset. The behavior of resetting the rename map table is parameterizable. The first option is to roll back the ROB one row per cycle to unwind the rename state. This is the behavior of the MIPS R10K. For each instruction, the stale physical destination register is written back into the map table for its logical destination specifier. A faster single cycle reset is available. This is accomplished by using another rename snapshot that tracks the committed state of the rename tables. This committed map table is updated as instructions commit. Okay, we're close. Causes. No water and no gum. Anyways, causes. The RV64G instruction set. What was? It's oh. Okay. Instruction set architecture. It's arithmetic logic unit. ALU. This is okay. So this is basically how you write assembly for that chip. Load store unit. You have your page faults. You have your branch unit, misaligned fetches, decode the stage. All other exceptions and interrupts can be handled before the instruction is dispatched to the ROV. Note that memory ordering speculation errors also originate from the load store unit and are treated as exceptions in the boom pipeline. Actually, they only cause a pipeline retry. Point of no return. The point of no return head runs ahead of the ROB commit head, marking the next instruction, which might be speculated or generate an exception. These include unresolved branches and untranslated memory operations. Thus, the operations ahead of the commit head and behind the PNR head are guaranteed to be non-speculative, even if they have not yet returned back. Currently, the P point of no return is only used for ROCC instructions. ROCC coprocessors typically expect their instructions in order and do not tolerate mis-speculation. Thus, we can only issue instruction to our coprocessor when it has passed the PNR head. Alright. We went down a rabbit hole, but you have your exceptions, flushes, you have the commit stage, you have your LSCU. Let me bring this. Is this a maximum? Yes, it is. Alright, PC storage. The ROB must know the PC of every in-flight instruction. This information is used. Any instruction could cause an exception in which the exception PC, EPC, must be known. Branch and jump instructions need to know their own PC for target calculation. And then jump register instructions must know both their own PC and the PC of the following instruction in the program to verify if the front end predicted the correct JR target. Alright. Most out of order CPUs use a reorder buffer ROB to ensure in order retirement. The ROB is a list of in-flight instructions being tracked in the backend and is kept in program order. Reordering capacity can be capped by the ROB size if no other resources are exhausted first. A73 doesn't appear to have such a structure. NOPs are a good way of finding ROB capacity because they don't take space in the register file, load and storage queues, or other more specific resources. They are just an instruction that does nothing, taking up a ROB slot, but NOPs have basically infinite reordering capacity even past an unresolved branch. I also extended Harry Wong's technique of combining inflow writes to the integer and FB register files by mixing stores in. At that point, A73 can track 76 in-flight instructions, showing that I'm not hitting reordering capacity limit even when maxing out 3 separate underlying resources. There is a particular practical limit of about 76 instructions with the store queue and register files utilized to their maximum capacity. Final words. Out of order retirement is part of ARM's strategy to maintain good performance with smaller core structures. In a sense, it's good and similar to that of Skymon's 16Y retire stage. Both cores are trying to deallocate resources faster, letting them achieve a certain level of performance with the smaller internal core structures. As mentioned in the prior article, that makes A73 a fascinating architecture. Alright. But when A73 has to lean on its core structures, it's often at a disadvantage compared to A72 or A57. The question then is whether out of order retirement is effective enough to keep A73's performance competitive. Certainly, in some cases, A73's strategy works well and gets it very close to A57. That's an impressive feature considering how much smaller A73's structures are in certain places. Library X264 encoded is an example of this. Other cases aren't so clear though, and file compression is a counterexample. Instructions per cycle, you have library X264 transcode to 720p, and you have your decompression. Okay, so is he running compression algorithms to test this? Library X264 transcode to 720p. What is this? Oh yeah, so that's a transcoding for videos to control the quality of it. Alright, so what was the point of this graph? Because how much smaller are in library X264 encoding is an example of this. Other cases aren't so clear, and file compression is a counterexample. Alright, so A73 does worse for 7-zip compression. It does 0.85 instructions retired per active cycle, but A57 did 1.06, but it was always the same thing. Maybe it was the chip smaller. A53 versus A57. I'm not sure. But IPC is only part of this picture. It's all too easy to tunnel vision on IPC. Inter-process communication. Okay. It's only part of the picture. It's all too easy to tunnel vision on IPC and lose sight of the forest. Clock speed matters, and A73's lower power withdrawal lets it reach higher clock speeds than A57. The Amlogic S900-222's 4 A73 cores run at 2.2 GHz and can stay there with passive cooling. The Tegra X1's 4 A57 cores run at 1 GHz and don't go faster even though the Nintendo Switch has active cooling. Alright, thus A73 is able to provide comparable performance and lower power. It does so by running a smaller, narrower core at higher clocks. A73 is a reminder that building higher IPC architecture is not always the best way to go. The same applies to targeting higher clock speeds. Both strategies can do well, and both can fail depending on how well engineers balance the core for the application it has to serve. If you like, okay, that's good. Clam Chowder wrote this. Alright, so it's a lot of new information for me, but okay, let's just reiterate on it. So out of order, you have in order execution out of order. You use reorder buffering to do out of order superscalar parallelism. That's basically executing a bunch of things parallelly, even though they are in series. The instructions are in series, they are dependent. I don't know how that works. Alright, so however A73 can perfectly allocate that. A Cortex, you have that. So you can see the difference here. You have the unified register file, but now in A73 you have it load data to a floater point neon register file 78 is to be 128, and the integer register file it's about 73 in 3 8R3W ALU integer multiplication branch fuse multiplication add what else? Memory ordering rules. Stores cause another problem for A73 besides taking up valuable space in a small structure. A73 doesn't have a way to speculate whether a load will be dependent on a prior in-flight store. That means loads can be executed until all prior store addresses are known. Alright. I see. Yeah, so let's go to the Cortex not so infinite reordering capacity. So I guess they resized the CPU, but at the same time it costs some performance issues. And in order, front end brings instruction into the core. The rename allocate stage assigns backend resources to the instruction. Rename allocate stage. So when you probably get the instructions, you have to rename and allocate them. And then you have front end, you have a back end. Then the back end calculates results for those instructions without waiting to know whether the instructions actually need to be executed. These speculative results are contained in various internal core structures until they are known to be good. Register values are held in the speculative portion of rename register files, and values to be written out to memory are held in the store buffer. Final instructions can be retired, leave the core when they have passed all checks, and all instructions before it have also passed their checks. On retirement, register values are made program visible and pending in store data is written out to the memory hierarchy. Retirement also frees entries from internal code structures, making them available for newer incoming instructions. Therefore, how far a CPU can move past stall instruction is limited by how many entries it has in internal structures like register files, load store buffers, and so on. Okay, so you can see the conventional way used to be load cache misses retirement, but in Cortex A73 you have your retirement unit bypassing an incomplete load, and then the adds are registering file entries for newer instructions, and then add and then load cache miss integer register file capacity. Cortex A73 detects UWU limits. You load branch add and add retirement until bypass. Okay, so So I feel like in Cortex, if you have an incomplete load, shoot. Your backend cannot accept instructions past this point. But in Cortex A73, you have a way to bypass this. Okay. It kind of make some sense, but how do you bypass it? And when you bypass it, how do you know your bypassing is fine? It's achieving the thing that you want to achieve. Huh? Is that a fair question to ask? How long is this video so far? Alright. I'm not very good with these clear tapes. My bad. Alright, so I'm going to read 2 more of these articles and then I let this sink for now a little bit. Might just watch this video myself so I refresh my memory, but I'm gonna finish this video right now. Thanks for watching so far. And then hopefully we can get a better understanding in the next videos. Alright.